Okay, anyway, I think we can start. I think we will make it brief. If anyone has any questions on the go, like feel free to answer. Feel free to ask, and we can discuss. So yeah, I think I need to. Each time when I try to make a presentation, I always forget about like where the presentation mode is enabled.
Slideshow.
Yeah.
Top right.
Top right, yeah, yeah.
Oh, yeah, because I always start looking at here and yeah, but it's actually here. So yeah, like today we have like a workshop about like that is called like LSTs for the modular stack, which is yeah, technically we will talk a bit about LSTs, but they won't be like our main topic of discussion today. But actually, like on the example of the like liquid staking protocol, we will talk a bit more about how to make like secure applications in the like modular world. So what the state of the problem, right? The future is modular, right? We are on the Modular Summit today, and what we mean by that is that basically like we don't like see the single chain that fits it all. We see that we have a lot of approaches like to build different applications, like blockchain applications based on the like rollups, Cosmos SDK chains, like completely different things. And yeah, so like what we see is that probably we're not gonna live in the world where like we have only a single chain that that fits for everything, but probably we're gonna live in it like in worlds where like there are multiple chains, they interact with each other somehow with bridges or something. But anyway, so we need to like move towards this direction, so to say. And yeah, and to live in this like interchain, like modular or interchain or whatever world with like a lot of blockchains, we need to like build the interchain protocols, right? Because like liquidity is fragmented, like the user base is like distributed across all of those like blockchains. We need to build some sort of like integrations between them. You're not like really interested into limiting yourself in the like one particular ecosystem, right? So you want to build like real cross-chain applications, like, and it should not be like probably like just like copy pasting the application that you have on one network to another, and have it like there to like to fragment the liquidity like even more. You probably want like some applications that can interact with other applications on the other chains and such. So like here is like the illustration here is the example of like the map of zones, which is like one of the, yeah, I mean like in terms of like illustrations, it's one of the like good examples. It shows like only the Cosmos ecosystem, like but we can imagine that besides the Cosmos ecosystem, there are even more applications that like your application want to interact with. So yeah, that's what we have. That's what we see as a thing right now. And yeah, like one of the like platforms that is trying to solve this issue is Neutron. It's the Integrated Applications Network. So Neutron is a blockchain built on Cosmos SDK that is trying to solve like as one of the issues that it tries to solve is that we want to build like cross-chain applications, right? That want to interact with other chains and such. And sometimes we can build them as like a separate app chains, right? So like for like you can just build your blockchain with Cosmos SDK or whatever else platform, like whatever else SDK you want to use, and bake all the logic into your blockchain. I don't know, like integrate some oracles and stuff, whatever you want to use for that. But sometimes we don't really want to use like to have an upchain, right? Because like upchain has a huge technical overhead. We need to manage the validator set. We need to care about staking. We need to care about consensus. Even if we are like taking this stuff from Cosmos SDK, right? So we use like Tendermint and such. We anyway should care about it. Like we should care about the all the like possible issues, like including like vulnerabilities, like upgrades, whatever. The upgrades of like Cosmos chains, for example, are pretty like still pretty so to say, stressful events, right? So yeah, and Neutron solves this issue through building a platform that allows your smart contracts that are deployed on Neutron to be as powerful as an upchain, right? And to utilize the IBC stuff, like interchain accounts, interchain queries, and such, and build the applications with smart contracts instead of building them as an upchains. And one of the examples of such application is Drop, is actually what we are working on right now, is the interchain liquid staking protocol that is built as a set of smart contracts on Neutron, and it's this protocol works in a way where we have the head of the protocol deployed on Neutron chain, but stake is managed on other chains, right? So basically, what Drop does is you provide your tokens to this protocol on Neutron, but your tokens are staked on the other chain, right? And it's done through the interchain accounts from IBC, right? So. But what does it mean? It means that we have a little bit of the smart contract development paradigm shift, right? Because we got used to the from the very beginning of creation of smart contracts. We got used to the model where when you develop your smart contract, you have the transactional model of changing the state of blockchain, right? And if something goes wrong, you can it works in a way where you just fail the transaction, the state is reverted, and you're pretty safe, right? So basically, it works in a way where you can rely on the transactional model of the blockchain itself and be sure that everything will changes consistently and such. But if we develop the smart contract that interacts with something external, right? So as an example of Drop, we have a smart contract that wants to stake assets on the remote chain, and to do so, our smart contract need to issue the intent to do so, and wait for this action to be executed on the remote chain, right? So. And it's something that definitely doesn't happen in the single block, right? Because at the very least, we need to submit the transaction where smart contract tells that it wants to make this action, right? The relayer should pick it up, should submit it to the other chain, which is already takes time, and in the very optimistic scenario, it's at least 1 block away, right? This action should be submitted on the other chain, should be executed there, and then the relayer also should take the result of this action and submit it on Neutron chain, right? So between the the smart contract's intent to do the action and between the actual callback that's happening on Neutron, there are several blocks. At the very minimal, it's a single block. Everything goes blazingly fast. But what does it mean in terms of smart contract development? We don't we don't have anymore this ability to just roll back the state if something went wrong, right? So for example, if this thing would be one transaction composable, if anything goes wrong on the remote chain, we could just fail the transaction if it's if everything happens in one transaction, right? We could just fail it and the state would be reverted and we would not care about it at all. But right now, we have at least some time where a smart contract stays in the state of awaiting the remote action to be performed on the remote chain, right? So, and this that means that interchain brings us asynchronicity, right? So we have to deal with a synchronous environment in smart contracts, which is not very the thing that is smart contracts are built for. And yeah, it started looking sort of like an enterprise classic backend development. So our smart contract actually right now performs some sort of a microservice that does some asynchronous works and such. But it's still a smart contract, right? Like we still have the limitations that we have from smart contracts. We lose some powers that we got from the smart contracts and the blockchain, right? Because we cannot reverse the state this easily and such. And we get some drawbacks that we have from smart contracts. Not the drawbacks, but sort of like features that they have. So for example, we cannot fix smart contracts shortly because if we're talking about like decentralized applications, they are usually performed by like DAOs or maybe they are completely permissionless and have like no ability to upgrade the contracts or something. So like it's not the case of like production applications like from Web 2, right, where we can just like connect to the like production via SSH, fix something, like if something goes wrong, roll back the database, like I don't know, like have a snapshots and so on and so forth. It's still smart contracts, like we cannot just do it. We should be much more like they still require us like to be much more careful with the development, much more paranoid with the development. We still need to build them in much secure way. So like we see that the complexity of application is getting closer to what we had like in sort of like in Web 2, but we still in this like new reality where we have to care about security much more than we used to do it like in Web 2, so to say. And yeah, and so how we can approach that? Okay, like let's build the protocol as a final state machine then, because like it's a very sort of like obvious approach, right? So we have some application, some program that acts asynchronously, right? And we need to somehow manage the complexity of this thing, right? So like it's not enough to just like code it. We need to have some spec that tells us like how this protocol should work in the very formal way, and we need to manage this complexity because like here is like the final state machine of the core smart contract of drop protocol, right? And it's a pretty complex thing, and it's because like we have to do a lot of stuff to do on the remote chain. So what drop does, right? And it's reflected like here on the scheme. I won't go very deep into it. It's not the topic of our discussion today, but just like to have like the understanding. So like we have we have to withdraw funds that are being unstaked on the remote chain so that they could be transferred to user. We need to claim the rewards, right? Because we want to stake them again. We need to stake the assets that were deposited to drop protocol on Neutron on the remote chain, so they would be staked eventually. We want to stake rewards that we claimed before, and we want to create new undelegation requests that were made by the users, and we like gather the batches of this and such. So there is a lot of stuff that we want to make on the remote chain, and even if even while we have like interchain queries where we can get like information from the remote chain very in a very permissionless way, we still need to be very careful with these like remote chain operations, right? Because it's still a remote chain. We cannot just query its state like whenever we want to. We need to the data that from that chain need to be submitted to our chain by some external provider. It could be it's completely trustless because of ICQ, but it's still pretty complex task, right? So we need to be really careful while we are building that. So yeah, and what we get at the end of the day is like think of that complexity, right? But okay, so we build our protocol as a final state machine that works in a way where, so basically like on this scheme, like circles are the states where smart contracts awaits for execution, right? So basically all the transactions for core smart contract, they go from one circle to another circle. It's the actions that are performed during the transaction, then it goes to it emits some interchain action it wants to do on the remote chain, and then it awaits its execution on the next circle. Once the action is performed, the result is submitted, we get the new data from the remote chain, then we can call smart contract once again, and from this state, checking if everything is okay, it will go to the next step performing another interchain action and such. So okay, we built this like specification for final state machine, and we implemented everything in Rest. So basically, like drop protocol is implemented in Rest with the COSM-WASM. But yeah, but what can we do about it next? So okay, like final state machine is a pretty mathematical thing, right? So like it feels like it should be formally verified. And yeah, like here we can go like with Quint. It's a like great tool implemented by the informal team. And we can build a model of this state machine. We can like set some invariants we want to check and such. We can run like a lot of tests on that state machine. So yeah, like we can implement this state machine as like as a Quint model. We can like prove some properties of this machine. We can also prove some properties of this final state machine, like just purely in a math way, right? We can just like build strong mathematical proofs for this state machine. And yeah, like we basically like this object, this artifact that we had, like is a pretty formal thing, right? So like we can work with that in a pretty formal way, and we can prove its correctness and such. So yeah, like it's a pretty good thing that we have it. But we like at the end of the day we have like these three objects, right? We have the spec, we have the model that we built with like math proofs, Quint, or any other tools that we can use, and the code that we implemented for this spec, right? And the relationships between like spec and model, they are pretty straightforward. I mean, like we can examine it just manually. Like it should be clear. The model should be built in a way where like you can just like yeah. So you can see that the correctness, like the model is implemented properly, just because like it's the requirement for this model in the first place, right? It should not have like a lot of boilerplate related to the actual implementation. So it should be like pretty straightforward for us that, okay, like let's imagine that like, yeah, spec is completely reflects the model that we implemented, or vice versa, like the model reflects the spec, right? So that, yeah, that is good. But the next question is, okay, like, but the code that we implemented, does it really correspond to spec? Because, like, this final state machine that we had in theory, like, it's a great thing that we have it, but the question is, does our code actually reflect the state machine that we implemented? Because our code is like built with COSM-WASM. It's yeah, like we don't have like good libraries to build final state machines there, right? We don't like really, we have a lot of boilerplate related to the interchain accounts, interchain queries, all the other like technicalities that we have here. So the code is pretty complex itself, and like building this relation between spec and the code is not that obvious. So like it's not clear for us whether like this code is actually corresponds to the spec that we like meant to implement. And yeah, and here we talked only about like the spec and the code, but at the end of the day, when we're talking about the protocol correctness, like when we want to say that, okay, like we proved some security features of the protocol, actually, that is what like we are interested in, like whether like model corresponds to the code. And here is like it's much less clear, because like we don't like, if we could have like at least this relation, we could say, yeah, like at least these two things that they implement the same spec, and that's okay. But since like this one is not obvious, this was like it's not clear like whether like they have any relations, like whether there are any relations between them at all. And ideally, we would love to build like this dependency in the first place. And yeah, like and yeah, that's what we are concerned about, right? Because at the end of the day, the implementation matters, right? The implementation is the thing that works actually on chain, that like faces all the potential issues with liveness and safety and security. This is the thing that is going to be like attacked by hackers or whatever. So like implementation is something that we care about. So like it's not enough for us like to just build a good model and to say that, yeah, like that's good. We need to actually like check whether this like code actually corresponds to this model, or at least like through its relation to the spec. So, okay, and someone could say here, yeah, like we have carry forward correspondence, like we can just build our protocol from scratch with the formal tools, like, I don't know, like prove its correctness with Coq language, something like that. But yeah, like, but let's be honest. It's a rare case, right? We actually like rarely the like protocols in crypto, they are ready to build their stuff with some like really complex tools with the high learning curve, like, and so basically what like crypto like space is like has a really fast pace, right? We need to build fast. We need to prototype things. We need to go to market. And yeah, like we have no time to, I don't know, like let's re-implement everything in Coq so that it would be like 100% secure. Everything would be formally verified. And even like here, we will face a lot of issues related to the fact that our execution environment is not that good yet, and CosmWasm itself like is not formally verified anyway. So yeah, like there is a rabbit hole, right? So what we need at the end of the day is some sort of like a simple solutions, right, that would allow us to apply all of those like formal verification stuff after the protocol is implemented, actually, right? When we already have a prototype, when we already have something working, when we already like tested some hypothesis, we already like figured out some potential issues and such. So yeah, like that's how it works, right? It's an iterative development at the end of the day anyway. So, and yeah, and we should be honest with ourselves, right? That actually like like when something is already implemented and we already have a prototype and such, and we are at this point we already want to go to market pretty soon, that's the step where most of the teams, they start to care about security and such, and like start doing audits and so on and so forth. So that is why like we need something that will help us on this stage without like rewriting everything from scratch. So okay, yeah, and here's the like basically the main topic for today is like the solution that we implemented in our project to actually try to approach this problem is, okay, like what we have the code that implements something, and we have a graph of final state machine. In the first place, what we did is like we formalized the graph, because like the graph that I showed you before, it was like just drawn is like draw.io thing, right? It's just like manual things that you can use for building something. You can take a look at it, you can modify it, but it's not something that we can work with from the code, right? So the first thing that we did is we formalized the graph first. It looks like that now. Yeah, so like we implemented it, like we basically like described all the, made this description of this graph in .lang that allows us to basically build graphs and visualize them. And the good thing about it that, yeah, like, so basically from this graph specification written in .lang, first thing that we can do is we can build the visual representation of the graph. So we can examine it manually. We still can work with that, like for our like model building proof, like the proof of some properties and such. But the most important thing is that we can parse this description, parse this graph specification, and work from that from the code, right? And it allows us to build the tools that actually like analyze this graph somehow. And the second thing that we did is we added the code traces. So you can see that, yeah, I'm gonna take a step back. You probably cannot see it, but like all of these nodes, they are enumerated, right? So each node has its own unique ID, and we want to preserve this uniqueness with like backwards compatibility when we will work on the improvements on the protocol. But yeah, like each node has its own unique ID, like in our since our code implements this specific graph, in the code we should see the places where like each particular node is implemented. And basically what we are doing is a pretty simple thing. We just put the traces of those nodes like into the events of transactions. So basically we're like whenever we do any action, whenever we go from one state to another, like basically like any like state transition in terms of like this final state machine leaves a trace in our code that is like corresponds to this specific action. So we just like pushed like the event with like the keyword not and the unique ID of the final state machine node that we mean to implement here. And what does it mean is that like whenever we execute any transaction, for this any transaction, we have the set of events with this like keyword and the unique ID of the node, and we can match this trace that we got from the transaction with the graph that we have. So we just like for any transaction that we observe from our protocol, we can take this trace, we can match it to the graph of our final state machine and check whether this trace is actually the correct path in this graph, right? Because if it's not, then it means that our protocol, our code actually does something different. It does not implement the final state machine it's meant to be, right? So yeah, and that's how we can prove. It's not like the strong proof. It's a pretty weak proof, but it's much better than nothing. That's how we can prove that our protocol that is, you know, like written in like Rust with all the boilerplate, with all the stuff related to COSM WASM itself, with all the like workarounds around, I don't know, like interchain accounts and such, with all the asynchronicity, all of this stuff, it still implements the machine, the final state machine that we created like for our spec, all right? It's not the strong proof, but but it's first of all it's the proof, and we here, like when talking about the correspondence issue, we basically transformed the issue of manual examining of the all the lines of code to check whether they implement the final state machine manually, to just like a simple task. You just need to see whether this like trace is emitted like when the action is performed, like when the proper action is performed, and that's what you need. So you basically have you have much easier task to do to prove that your protocol is correct. So yeah, and when we can check this correspondence, like we can check it whenever. We can check it during the unit tests, and here you can see the example of unit test. And this is the good part of it as well, because like for example, in our unit tests, we have this like check in each test, and basically it means that for each unit test, we actually see which path in the graph this test covers, right? So like we can see whether like some path is covered, some path is not, because without that it would be really really difficult even to explain which specific path you want to cover, like when you create like a task for developer or something. And here you're just saying, hey, like this path is not covered in our unit test, just write a test that covers it, and like it just can be done, and you can like see that, okay, like yeah, this thing is like exists in our database, in our code base right now. We can do it during the integration test. So like whenever we launch the like local environment for testing contracts, we can like for any action that we do, we can check, like we just put a checker that for any like transaction actually checks whether these like transaction events they lay in the graph, right? And we can do it like for testnet and mainnet environments as well, right? So whenever we deploy our protocol on testnet, we implement the monitoring that like just like indexes all of those transactions, and once again checks whether they implement the correct thing. And if we see that something goes wrong, like we actually know that, okay, yeah, our protocol started to behave in a weird way, and we need to fix that. Because once again, like, yeah, we never know that, like, whether we covered all the potential cases, right? Like, even if we see that all the transactions before they generated proper traces, it doesn't mean that there will be no transaction in the future that will generate some weird trace. So yeah, like that is why we need to put it into our monitoring as well. And yeah, that's basically it. Yeah, you can follow the progress of our project on like the drop.money website. You can follow our Twitter there. You can check the repos, and we are working hard on publishing the docs as well. And yeah, we are going to be launched pretty soon in a few weeks. So yeah, thanks for listening. Happy to answer any questions.
Actually, maybe I think I missed this, but like, what's the advantage of implementing the FSM in your protocol, and like, why are people, like, what's the alternatives to like checking whether the app is running well?
Yeah, thank you for the question. That's a good one. Yeah, so what the advantage of implementing is FSM, because basically we need to manage the complexity of it somehow, right? So that's the question of how we can like create that. And to be honest, like there are at least like 3 protocols building on Neutron right now, the protocols of this type that interacts with something on the remote chains through the ICA and such. These protocols are Drop, the Covenants by TimeWave, and the AMOLED protocol. And yeah, we talked with all of them, and we see that all the teams, they come up with the final state machine idea at the end of the day. So it's the, like, it looks like it's the like best trade-off in terms of like managing the complexity of this protocol, and like the only way probably to do that, because yeah, like you anyway have very like the states, they appear in your protocol in a very natural way, because you have to stop execution somewhere and wait for something to happen on the remote chain, right? And and wait for the acknowledged the result to be submitted. So the states where protocol sort of pauses its execution, they appear very naturally. So final state machine looks like the very natural way to implement these type of protocols. So yeah, I'm not sure whether there is any good alternative approach here, because as I said, yeah, from what I saw, at least from our experience and the experience of teams we talked with, is yeah, that final state machine approach is the very good one. The alternative, what could be the alternative solutions for checking the protocol correctness? I mean, it's not about the alternative solutions, but the complementary things that anyway are needed. We will also, of course, we write the test, like unit tests, integration tests, and such. But if we are talking about the protocol correctness in this specific meaning, right? When we're talking about final state machine and whether this protocol implements this final state machine, I would say that yeah, first thing that I said, it could be implemented with some special tools for formal verification and such, so that the protocol correctness would be just proven by these tools, but we are not yet there. So yeah, we don't have the necessary tooling and such, as far as I know. At least for crypto, it's not yet implemented the tool of that would be this advanced for CosmWasm. But yeah, the other potential good solution here would be if we could have any sort of standard framework to build like for example, final state machine. So for example, yeah, like I mean, it looks like on our experience that all teams that are start doing like the protocols of this kind, they are building final state machines at the end of the day. And it means that probably this approach could be generalized somehow, and we could have like these like SDK either baked like in CosmWasm itself, or maybe like as a standalone SDK that would allow us to actually like structure our code as this final state machine. So we like in the code we actually would describe like just like states, the actions for transfers between them. And all of this sort of stuff. And if we could have like the SDK of this type, then it would help us with understanding like it would be much clearer just like with like the manual examining of the code that this code actually implements this state machine, because like you have one-to-one correspondence with all the artifacts from your graph in the code, but it's not the case yet unfortunately. Of course we thought about like implementing something like that maybe later, once we will have enough experience with working with that, because we need to understand what our actual needs from this framework, from this potential framework. But it's not the case yet. So yeah, but it would be a great solution as well, so that we could just like structure our code in a proper way.
And right now the limitation is the Cosmos SDK,
CosmWasm. It's not like, it's not the limitation, it's just, like we, as I said, like Neutron here like brings like this new approach to life, right? Because like we didn't have this feature in Cosmos yet. So yeah, like only on Neutron we experiment with this kind of stuff in CosmWasm. So it's not like the CosmWasm limitation, it's just, like we're experimenting with a new field. So yeah, like we just haven't managed to implement something for that. So as I said, like based on our experience, I think that's a potentially good thing, like to collaborate with all the teams that build such protocols to see how we can like make it better for other teams to work with that in a more simple manner. Yep. Any other questions?
Have you seen anything like that people are building for rollups that has kind of similarities with this?
I'm not a blockchain developer, so I don't really know like what's other solutions out there. I think like makes sense in terms of like checking the states. I'm a developer, but more like Web2 developer. But I mean, there's probably like other smarter ways of doing like the proof of the event happening. And from what I see, FSM is very, very like logical.
Yeah.
But maybe there's other ways of doing it.
Yeah, that's all kind of new. Yeah, we're also curious, I would say.
Yeah, that's probably the case. Yeah. So basically, there are definitely other ways to do that. Like this one is just why I think it's important, because this one is like really easy to integrate into your projects, even on the very like late stages, right? Even if you are already implemented everything, if you just at this stage you started thinking about, I need to like, even if your project already live, right, or already like deployed on mainnet, you can add this stuff, and even it won't break your logic or something. You can like even upgrade your smart contracts to this version with just like additional events being emitted that won't break anything, won't like introduce any new vulnerabilities and such, and gain additional security, right? That's also like pretty important property of this approach, that it's like really easy integrated.
And it always goes back to the idle event happening, or the idle state.
Yeah, yeah. It's in our case, yes. In our case, yes. So basically, yeah, like we have these like idle state here, but it depends on the structure of your protocol. So basically, yeah, for us, like it's idle because like we want to make actions on the regular basis here, and like we want to have like the gap between those actions. So that's the place where protocol just awaits like in idle state unless like until the timeout is reached. So that's just like the specific detail for our protocol. But yeah, it's not a necessary thing, I would say. Yeah. Yeah. Thank you.
Cool.
Okay. If no other question, I think we can wrap it here. Perfect timing.
Thank you guys.
Yep. Thank you everyone for coming on this rainy day.